Let's think about some tricky issues about summing the series that a student was asking about. Let's start with something that is true and useful, and that's just summing two series. If I have a series, an infinite series, a1 plus a2 plus a3, or in other words, with summation notation, the sum of a sub k, and then the sum of b sub k, and I have the sums being a and b, well then what about if instead of doing this first and this first, doing that whole infinite sum process first and that sum process first, I group the terms together. I sum a1 and b1, and then I sum a2 and b2, and I sum a3 and b3, and then so on. And so in other words, it's the summation of ak plus bk. And I call that C. It'd be nice if C was equal to A plus B. And we should always be suspicious of those kinds of results, because infinite sums aren't just really sums. They're a sum plus a limit. And limits can be very tricky if you're not careful with them. Well, the answer, this is in any calculus textbook that talks about series, and it's certainly in our textbook. And the answer is yes, if A and B, oops, just kidding. Somehow I did a insert there. And B both exist. If these limits actually do exist, then yes, we can sum them up. And we use that all the time, especially when we look at power series and things like that. So what's the proof of that? Just real quick, it's in the text. But you always, to prove those kinds of things, you always have to take it back to the to limits. So by definition, C is the limit as n goes to infinity of a finite sum. This is where it's really handy to use the summation notation, although it's not as friendly as using dot dot dots. So this is the limit as n goes to infinity of, well, it's basically this, but we cap it off. Yeah, I'll put it in parentheses. Plus, and we call the last term n. Okay. And so those are the terms in the sum. And so one issue that was raised was, does the numbering matter, or exactly what the sequence is? Does that matter? Well, to make it well defined, to make any infinite sum well defined, you have to actually say what the sequence is that you're talking about, that you're actually summing up. And so in this case, if for any particular value of n, you sum all these up, all the a's through n and all the b's through n. Now, of course, the part of the point of this, the way this proof works, is that is just going to be. Let me copy the whole thing, the whole darn thing, because I want to work with it in parallel. Okay. This is a finite sum of sums, and so all of our principles of associativity and commutativity work there, and so this can be broken up. And so this is just going to be the limit of those two sums separated out. Or in other words, at this level, I can reorder everything, and I can change this into A2. Sorry about the coughing. I know that's really annoying when you're listening to this, especially on headphones, because I'm listening to it on headphones and I don't enjoy it when I cough at myself. Okay, plus B1. Well, let's see. So plus dot 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 plus. Now remember, the dot dot dots here kind of hide the pattern, but they're not nearly as dangerous as a dot 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 that just trails off and is expected to go off to infinity. Oh, that's a piece of it. Okay. I don't really need all this stuff, do I? Okay, you get the idea. Okay. So, because this is a finite sum, and this is a finite sum, those are exactly the same finite sum, and it's completely well defined what the pattern is that we're summing up, those are equal. Okay. And that's going to be the limit. So the limit, now here's the tricky part. It's when the limit does something is when we really use something interesting. The limit, this is a sequence of partial sums. This is S1, S2, S3, S4 for the A's. This is the partial sums for the B's. And so I've got a limit of the sum of two sequences. And exactly when those both exist, when those limits both exist, that's when we can break it up into the limit of the sum of this guy. Let me break that. Plus a separate limit of the sum of this guy. And over here, that would be in just a little more friendly notation. Oh, come on. I didn't mean to do that. I didn't mean to control C here. There we go. So that's the limit of the sum of this guy. Boop. That's still not what I meant to do. Okay. Plus the limit n goes to infinity of the sum of all this stuff. And those parentheses are horribly mismatched now. Okay. And that's good enough. Okay. So that, you've got the limit of a sum is the sum of the limits, and that's where we're assuming that these limits actually do exist, and that's just a plus b. And so it really works that the limit of a sum is the sum of the limits. So the key ingredients were that all the limits involved existed, and so that when we did something with the limits, that worked, and that we knew exactly what pattern we were summing up, and that the pattern did what we thought it would do. Okay, so now the reason that we got interested in this is what was being asked about are these three sequences, these three sums. What about if you take 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 off to infinity? What if you group them, 1 minus 1 plus 1 minus 1 plus 1 minus 1 off to infinity? What if you group them with the 1 hanging off on the start, 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1? Well, let's see what these do. Well, here, what this means is you're supposed to do this operation first, the minuses, okay? In order, that's what parentheses mean. Do that first before you do an infinite sum. So remember, the process of doing an infinite sum means carefully tabulate what sequence it is, carefully tabulate the partial sums, take the limit. Okay, so this really is just 0 plus 0 plus 0 plus, okay, dot, dot, dot. And so because we've been told to take those first, we just get 0 plus 0 plus 0, and that's just 0. Okay. Here, we've been told to leave the 1 alone. So a sub 1 is 1. A sub 2 is 0. A sub 3 is 0. A sub 4 is 0. So that's 1 plus 0 plus 0 plus dot, dot, dot. And that's just 1. Okay. So these guys are not equal. The way of grouping does really seem to matter here. Now that should be, I think, hopefully contrast in your mind to what's going on here. Is that here, at least in some cases, we were able to group in different ways. That we could do the entire infinite sum of the a's and the entire infinite sum of the b's first, or we could sum them pairwise and then sum the whole result. But here, if we do something sort of similar, it's not good. Well, what's going on? Well, before we do this one, what's going on? The similarity here is, you could imagine, what's another couple of sequences we could do? We could try to compare this to 1 plus 1 plus 1 plus 1 plus dot, 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 plus minus 1 plus minus 1. Group all the ones together and all the minus ones together. Plus dot, dot, dot. Okay. What about that? Let me make it clear with parentheses here. That would be summing all the ones together and all the minus ones together. If this rule about summing series always worked, and you didn't have to worry about the individual sums existing, then this should work, and I should get, oh wait, but I get infinity minus infinity? Well, okay, that's already suspicious. Okay, this doesn't make sense. So certainly, this would be the most direct analog of the sum rule for series, and this doesn't make any sense at all, because neither of the individual ones sum up. Okay, but that's not exactly what we're trying to do here. It's not so radical a reordering or a regrouping. We're really just kind of regrouping the neighbors differently. And so, why isn't this working? Why aren't they giving the same answer? Well, another sequence that was brought up in this book problem that inspired this was, what about if you write it this way? Well, let's see. It seems to be that these three are kind of just the same thing if you're not careful about your parentheses. Well, if we have to assign to a meaning to this on its own, then what can it be? Well, I don't have any parentheses, and so I'm going to have 1, and then 1 minus 1, and then 1 minus 1. So it's the limit as n goes to infinity of the following sequence: 1, 0, 1, 0, oops, 1, 0. It keeps going back and forth. Okay, that doesn't exist. So this guy is certainly not equal to either of these. It kind of vacillates between the two answers, and that doesn't exist. But what I wanted to say a little bit about, if I have time, is there some situation where this does work, where this regrouping would work? Well, what's the general thing here? I claim we've got sort of two series here. So I want to group it into the positives and the negatives here. This way of grouping certainly did not work at all. But what if I look at the general case and I think about, when would this work? I have these sequences A1 alternating between A's and B's, and I either group them in this way, or I let the A1 hang off and I group them in a slightly different way. Are these ever equal? Are there conditions where I could assert that this kind of thing works? Since it's actually a less radical reordering than the formula that was true, then I would guess, or conjecture, let's be a little more confident, I would conjecture that this works if the sum of the A sub k's and the sum of the B sub k's both exist. And you could probably get away with less. I don't know, I'd have to think about that. But it should work if those sums actually both exist. So here would be a proof of that. We have to just write them both out as partial sums. Okay, so a partial sum of the left-hand thing would be A1 minus B1 plus A2 minus B2 all the way up through AN minus BN. Okay, and now is that equal to, because on the proof I did before, it rested on the partial sums being equal, and then you just took limits and made sure that you were careful about not taking limits that didn't exist. Is this equal to, let's see, the nth partial sum? Well, how do I make sense of this as an infinite series? I have to just make sure I know what the terms are. Well, these parentheses are telling me what the terms are. It's A1 is going to be the first thing, plus the quantity minus B1 plus A2. So do that first and make that the second term of your sequence, plus, and then end up with, well, let's see, what's going to be the nth sum of this guy? Well, that's the first one, so that it matches this 1. It matches the A term, and so it's going to be B sub n minus 1 plus A sub n. Because I have n's worth of A's, but I don't have n minus 1's worth of B minus 1. Okay. Well, those aren't equal. And this corresponds to something that the student I was talking to was complaining about, that he had an intuition that something was going on, that there was a B sub n that was kind of hanging off the end. So this is a way to kind of see that intuition has some justification. That if you try to prove this in general, in a way that isn't trying to pass through this thing, which is just completely bogus, okay, then if you try to prove it in this way, you see that at the finite level there is a problem. But that suggests that it's never going to work. But I claim this actually often works. Okay, and here's what's going to happen. So we know if we're assuming that these sums both exist, then we know that the limit as n goes to infinity of B sub n is equal to 0. Okay, so we're going to take the limit of both sides of this. The limit as n goes to infinity of this guy, well, let's see. Is that equal to the limit of this guy? Whoa, I didn't mean to put that inside there. Is that a period? Okay, I didn't want a period there. Oh yeah, it's extra. There's an extra period. Okay, so I'm going to take the limit of this guy. Goes off to infinity. All right. Well, let's see. Let me just go ahead and see what's the difference of these guys. The limit of all this will be the limit of all this minus what I'm missing is the limit of that extra b sub n. Okay. And now let's make sure this is real. Okay, I'm saying the limit of some quantity, this well-defined sequence of partial sums in this kind of weird way, minus the limit of this sequence should be the limit of the combination. Okay? Well, that should work, because if I actually put the b sub n in here, it will give me exactly this, just without the parentheses, with the parentheses changed. But at the finite level, that's fine. And the limit of a difference is the difference of the limits as long as everything exists. Okay? So I need to know that this limit exists, that this limit exists, and that this limit exists. So the part I'll fudge is that knowing that a sub k and b sub k, the sums both exist, really does tell you that everything involved here actually does, the limits are actually going to work. And you can make that rigorous. But certainly the piece that I put in here to fudge it to be correct, that is that limit does exist. And in fact, because the sum limit exists, the limit of the sums exists, we know in fact that actually the limit of the sequences has to go to 0. And so in fact, that just means that that can be deleted back out. And this works. Okay? And so in fact, this does work if they actually are all convergent sums in the first place. Okay? And so that intuition that the problem was that there was something hanging off the end actually doesn't really trouble you in a case where this is actually useful and correct, because whatever hangs off the end as you go towards n equals n goes to infinity, that vanishes in the limit. But it's definitely something we had to deal with, but it wasn't something that was actually a stopper. That's very much as opposed to this situation, where the reason this thing cannot be done, why we can't use this in the 1 minus 1 case, is that these individual limits don't go to 0, and in particular the limit of this sequence of the minus 1s definitely doesn't go to 0.